Okay, let's start the lecture of today. We have studied about the flow variability. Flow variability means the impact of the CV of the previous machines to the next machines, and that relation is being made by this equation. It means that the departure CV, it means the CD, is determined by the summation of the variability from the motion cycle time and also the arrival variability. And those two variabilities split into two terms. And if there is multiple machines, in that case we can use this formula that is induced by Bujakot and Shantikuma at 1993. Today I'm going to start from the first we have studied is process time variability. And there we have studied preemptive and non-preemptive outaging. Also, this flow variability these two variability have effects on the production line. It means that we have studied only the process time variability. It is the problem of is a single machine, and only have effects on the performance of the relevant single machine. But if the multiple processes are connected, then the variability of preceding machines have effects on the following machines. That is the flow variability. From now on, let's see the impact of variability effect on the main performance indices. Main performance indices is CT and WIP. Also including the throughput. But in our problem, throughput will be given. And also, in order to make a continuous flow lines, the arrival rate of the first machine will be determined as the same quantity as the throughput. from the textbook of factory physics, the actual process time typically represent a very small portion of the entire read time. Normally, the author have asserted that only 5 to 10% of the entire read time is being consumed by the process. So the majority of the extra time is spent on waiting, not working, for various resources. So, where this is the other, this is not the point, but this science of waiting is called the queuing theory that we have studied. Okay, now I'm going to review the several important parameters and also the performance index. And also measures. First one is the RA. This is the arrival rate. And as I've told you, the RA is the same with the reciprocal number of inter-arrival time. And one thing that important is in a serial line, without loss or rework, the RA will be determined as the given value of throughput. So this is very tricky and very important assumption that we are going to study. Second one is TA is the working time. Actually, this is the same with the reciprocal number of TE. Okay. This is the reciprocal number of the rate. Always the rate and time have a reciprocal relation, please remember. And again, C is shown representation of CV, the coefficient of variance. And CA is CV of the RA. And this is calculated by the standard deviation of the arrival time and divided by the TA. TA is And also we are going to define the number in our problem in this lecture. We are not going to adopt a heterogeneous property of multiple machines. We will continuously assume that the older machine that is belonging to the same process may have the homogeneous property. It means that all the same machines will be included in a same process. Next is we have the, please add this term, effective working time. Also, CE can be defined as like this. Now all of you will very familiar with this notation. These are the main parameters. And also we have to define several performance indices starting from FPN to CTQ, CT, also WIPQ and WIP. These are the performance measures. And firstly, Pn is the probability. The probability that there are n jobs in a system. CTQ is a expected waiting time in the queue, in the buffer. Actually, buffer means the queue of the relevant machines. And CT is expected time spent at machine. WIPQ is also expected number of jobs in the buffer. WIP is the number of jobs in this is not motion. This is the at workstation or workstation. It's also workstation. So if we draw a schematic configuration of with respect to these performance measures, so if we divide the entire number of if we call this configuration as a workstation, that the entire number of the jobs is called WIP, and only a fraction of the number of entire WIP in a queue or buffer is WIPQ. And also, the jobs, the expected time, then each jobs are waiting in the queue or buffer is Ctq, and also the entire expected time in a workstation is called Ct. And if we add the pre-process parameters, then this is RA, CA. So this machine has TEN, CE. Also, we can confine the size of the buffer, but we will not treat this model in this lecture. Anything is omit. Also, the number of machines in the process will be modeled as parameter M. Before the induction of the detailed means that actual problems, detailed process of how to calculate the main performance measures, we are going to the fundamental relations. When we are going to calculate the main performance measures, firstly, we have to calculate the utilization of the machine. And this utilization that we have studied as the RA over RE. But if there is multiple machines, then this have to be calculated by the number of machines. And if we calculate this utilization, then we can calculate the Ctq by use of this UN together with the another parameters. Also, this calculation will be different with respect to the kinds of assumption. But anyway, from this calculation, firstly, we have to get Ctq. If we get the Ctq, then after this, we can calculate Ct because Ct is the summation of Ctq and the effective working time. It is very natural, the natural relation. And also, if we calculate this Ct, then after this, we can calculate the WIP by use of Ritter's law. Ritter's law is WIP is equal to the multiplication of Ct and throughput. And in our serial production line, we will replace this throughput as RA, the arrival rate at the first machines, and insert this result here. In the same manner, WIPQ could be calculated like this. Here, the Ctq is going to here. In this serial manner, we can get all the required parameters. And this procedure is always same for the various kinds of problems. Now we are going to calculate a very simple problem. Actually, we have already studied these things, but this will be some review about what we have studied. It means that first problem is MM1. I will not induce the process of how each parameter WIP and cycle time is calculated with this problem. We will start from the here. We have studied this where is it? Wait a moment, I cannot remember where it is. I'm sorry, I cannot remember where it is. Anyway, we have induced the relation like this. This is the state of n is 0, n is 0, 1, 2. The increasing direction is caused by the arrival rate, and consuming the decreasing direction is like this. We have studied this induction, so I'll not go into detail today. Anyway, the starting point of this calculation, WIP. And from this WIP, we can calculate CT with this relation. Here. So from here, CT is calculated like this. And this can be rewritten and because of the CTQ plus TE is the same with the CT, so if we move this side, and if we add some simplification, then CTQ became as something wrong here. I'm sorry. This is wrong because here the U is in here, the number of machine is 1, so M is equal with 1. So this is divided mutually and only R remains. So the reciprocal number of R is TE. Okay. And this became like this. And lastly, WIPQ is the CTQ and multiplied by the RA. And if we insert this calculation here, and RA is RA. And if we insert here RA, then this becomes this result is very simple calculation. So this becomes U squared. Now, my use of this these notations, please calculate a very simple example. This is your work about tortoise 2000 that we have studied. Please let's assume the arrival rate is 2 point and the variability of the arrival rate as the exponential, and TE is, it means that the working rate is 3 per hour, and variability of the efficient working time also as well, because we are studying the MM1 model. This is very good example. Then please calculate the main performance measures. And the most important result will be the CTQ. Before the calculation, what do you think the result of the CTQ of this model in order to make a continuously flow line, seamless line? Simply, what is the number that required for the buffer? Please just think and tell me your thing. Tell me your number before the calculation. You can type in the chatting window just by using your intuition. Your expected number of the buffer size in this tortoise machine. What do you think? Please tell me. What is your expectation? No one? Okay, then please calculate the WIP, CT, and also WIPQ and CTQ. Somewhere tells the 1. The buffer size will be 1, do you think? Now please calculate the actual number by use of this formula. And if you finish the calculation, then tell me your result. It's not complex problem. You can calculate very easy way. Finish it? Finish or still calculate? Okay, now let's see the result. The first, that important, what is the first number? How about the number of WIP? What's your result? Please type in the chatting window. What is WIP? It's very simple calculation. WIP is just the calculated from the utilization. You are right, Hee-chang. It is 23. Then the WIPQ will be very easily calculated because this will be distracted from the number. But I will not use this method. We have to calculate this one. Then how about WIPQ? Samuel, what's the 22? Is it WIP or WIPQ?
WIPQ.
Q, almost same. It is the 22.04. So almost the same. Your calculation is right. Now, how about the cycle time? CT and CTQ. CT will be very easily calculated from WIP. How about CT? It's not complex problem. It is 8 hours and CTQ is 7.0. 6, 7, if we grade from 2 decimal point. So 7 point, in my calculation is 7.6. Summer's calculation is 7.8. Maybe there is some miscalculation in the decimal point, I think. Anyway, what do you think about this result? This machine, there is only one machine, and the arrival rate and the variability is not high. It's just exponentially distributed, exponential distribution. But the result number, WIP, is 23. It means that this simple machine have to secure the buffer with the size of 20, almost 22 in order to make the continuous flow line. Normally, the calculation result is very high because this WIP number is the maximum number that can be exist in the process of the working of this machine. But in the viewpoint of the production process designer, he or she have to assume the worst case. Okay, now let's go to the next topics about system with general process and the inter-arrival time. This can be defined as G1 with the candle notation. Most real-world problem cannot satisfy the assumption of MM1. It means that with the exponential distribution, the older manufacturing system cannot be modeled. It means that process time seldomly exponential. Also, inter-arrival time is unlikely to be exponential in real world. So in order to address the system with non-exponential inter-arrival time and working time, we have to consider the GG1 or GGM model in order to explain the real-world system correctly. However, unfortunately, we cannot compute exact measures for this model, GG model, the general model, without the memory list properties that is belonging to the exponential. So we have to estimate, or we have to approximate the performance measure by means of second moment approximation. This is the point. estimate parameters count G model. We have to use firstly, we are going to start with the approximation Ctq. So in this point, we will adopt the approximation result of the Klingman, who have studied about this approximation in 1961. And that result is like this. Ctq can be approximated. Ctq, how was the Ctq of the normal model? That is, this is here. Let's copy this portion and paste here. The performance measure Ctq of the MM1 model is like this. But in Klingman's research, he have concluded the Ctq of GG1 model can be approximated by multiplying the these terms here. By add these terms here, then the Ctq of general distribution model can be approximated very correctly. And here, each terms is called, first term is V, second term is U, and last term is T. Because first term represent the terms of variability. Because the consisting parameter CA and CE is the parameters from the variability. And second term is about the utilization. And third term is the time, only time. So sometimes this formula is called as VUT formula, VUT equation or VUT formula. So by use of this model, this relation, let's have some example. For this problem, we will add the pair x19 together with tortoise 2000. The property of pair x19, first the time variability is 6 and 5, but still the arrival rates, the CV remains as the 1 here. And effective working time is 1-3. It means that 3. It's same with the tortoise. Arrival rate is same, also same to A75. So we can calculate easily U because U is the installation. So if we this value and this value into this equation, the result is 0.9583 here. So let's see how big effect on the following motion. Following motion is 2000. Wait a moment, I will draw the model. This is hair, and this is tortoise 2000. We already know, what we know is that the sole result of the tortoise 2000, it means that the rest varies. WIPQ is, if only this motion works solely, but this will be different if we add pair x19 in front of tortoise. Okay, firstly, let's if we calculate the hair X19, I'm not going to let you calculate. Quickly, let's see the result. Ctq, wait a moment. Okay, Ctq of the hair X19, if we calculate this Klingman equation, if time is enough, we can calculate this formula because there are all the required parameters here. Already we have. Then the result becomes let's use the hour unit. The result is 27.8 hours. That is a very, very long time. Compared with the Tortoise 2000, it's only about 7 hours. But in case of hair X19, the waiting time in the buffer, expected waiting time, is very big. Because the variability is very big. This is belonging to the high variability region. Now, let's see how the Ctq of Tortoise 2000 is changed if the C departure CV of the preceding machines have effect on the following machines. In order to calculate this effect, we have to use the relation of flow variability. Do you remember this relation here? It means the CA2 means the tortoise square equal with the CE so we have to this will be same with the departure CV of the hair X19 like this. And this is the calculation result is plus 1 minus U square CA square of the hair X19. It becomes like this. And we know the utilization of hair X19. Also, we know the CV of working time of hair. Also, the CV of array rate of the hair X19. So if we calculate this formula, then it becomes 5.8261. Please calculate this after this class, please. Anyway, this is very big number compared with our assumption of tortoise 2000. What was the number of CA of tortoise 2000? What was the number? What distribution was assumed to tortoise 2000? It was CA. It was 1 because we have assumed the exponential distribution. But this is changed to over 5. And compared with the previous the value of CV, arrival CV, it becomes very high value. So now, if we are going to calculate the changed performance measures of tortoise 2000, now we cannot use the performance measures formula from the MM1 model. Instead, we have to use the second moment approximation. That is the Ctq, VUT formula. Then, so if we calculate of tortoise 2000 after the change of the CV of arrival, then blah 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 according to the calculation, this becomes 26.15 hours. It's very impressive number because that was only 7.67. When there was no preceding machines. But now, this hair X19 have impact on the tortoise 2000 with this relation. And according to this calculation, that impact have transferred to the tortoise 2000. And the result from this is very impressive here. So this is the mutual interaction. Actually, even though it is bidirectional, but along with this big impact means that the transfer of variability, then the result is very, very impressive. Actually, in the supply chain theory, there is very famous model. It is the chain reaction model. Sometimes we call it the bullwhip effect. Have you seen this bullwhip effect from that is started from the customer? Customer have order to the reseller, not reseller, the retailer. And according to the the order of customer, retailer have taken order to the manufacturer. Also, the manufacturer will predict the variation of the order from the retailer. And that is going to be what is called. We can make a subcontractor. Full heap effect means that the very small fluctuation in the downstream. If there is a small fluctuation here, but this small fluctuation will increase according to the expansion according to the supply chain. This is the mathematical representation of this full heap effect. Okay, the remaining topics is about the parallel machines. Until now, we have treated only single machines. But there is a case of parallel machines. It is very, very complex, but please don't worry, because the past researcher have already concluded about the final approximation. So let's see, only check the result of parallel machines. Firstly, let's see M1. Please remember, if we can calculate Ctq, from the Ctq, we can always calculate the other performance measure, WIPQ, WIP, and CT. So important performance measure is Ctq. In case of MM1, Ctq was right. Let's check. It is right. It's like this. But if the number of machine is not single, it means that if the number of machine is M, in this case, Ctq can be calculated by if we insert number 1 here, then it becomes this formula. Anyway, this work was conducted by Whit at 1993. It's not so long ago. And from this approximation, we can easily not induce, we can easily approximate the GM. What was GG1? We have concluded GG1 like this by multiplying these terms here. These terms. In the same manner, we can Ctq of GM can be approximated by multiply the same fraction, same terms here. So final result of Ctq about GGM can be calculated like this. This terms is inserted here. So like this. Also, there can be divided by variability terms, utilization terms, and working time terms. This is the final result. During this course of procedure, there is no analytic calculation. The continuous assumption, that it means the approximation, is conducted. But even though this is approximation, those value was validated in detail by the many previous researches. And also, even though this formula is very complex, but there is no integral or there is no differential calculation. So this can be calculated by use of a calculator or the spreadsheet. Spreadsheet means Excel, MS, Microsoft Excel. So let's see the simple example by exchanging the screen, sharing screen. I'll stop the screen and change it to the other, where is it? Where I have opened. Here, I'll share the Excel. Okay. Can you see the screen? Rina, can you see the Excel? How? Okay.
Professor, your mic is off.
Okay, now can you hear me? Can you hear me?
Yes.
Okay. Okay, the different thing is this one. It means that in this example, the product is moved together with this batch size. Also, we can determine the blue numbers. The remaining cells are calculated automatically because already all these kinds of relation was inserted in each cells. So we can conduct very simple experiment by use of this Excel. So in this case, the target throughput is 10,000. 10,000 product per shift. And that shift also can be determined. In this example, it was 8. But we, of course, we can change this number also. Also, the batch size can be changed. But if we insert 10,000 product per 8 hours, and products is moved by group as the size of 50, then the target throughput can be calculated in terms of batch. It means that 2.5 batches per hours is the target throughput. And now let's see here the machine parameters. Here is the number of the part processing speed per part. Very, very simply, if we divide this number, 10,000, by the shift number, in order to satisfy this system without the shortage, this system, each machine have to produce 125 products per hours. 125 number comes from the 10,000 divided by this 8. So at least each machine have to secure the bigger number of capacity, this processing speed, bigger than the 1 to 5. If any number of this machine is smaller than 100, 125, there will be some errors. Not errors. This system will not correctly operated. So I just input these numbers. Also, we can apply the CV of this effective process time. So a certain variable numbers were inserted. And also one assumption about the batch, this price is used here, so you can ignore these values. And number of units can be also changed. But please remember that if we change this number, we have to consider together with the machine processing speed. And from these parameters, the following calculation can be processed. Somewhere, have you calculated again and finally get the right number to 7.8? Okay, Good job. So in here, the squared CV was calculated in terms of the in terms of the batch. It means that this CV, let's see here, each CV of respect to the machines was calculated with the part processing speed. This is the effective working time. And not here, this one. The part processing time was calculated with this number. And also batch processing time was multiplied by this batch size. And important, the thing is here. The SCV, squared CV, is calculated by divide the single parts variability divided by the batch number. It means that if the products moved together as a group, then the CV is decreased. Actually, this is called Pulim effect. If the various product processed together, in that case, the CV, coefficient of variance, is decreased according to the number of batch size. So you can see here, the SCV of batch processing is decreased from this number here. Then unit utilization also can be calculated. Also, in order to use this spreadsheet, you have to insert the SC, the CV of the arrival at first machine. I just put the number 1 and can get these kinds of result. So I will give you I will upload this Excel spreadsheet in ETL. And please use by exchanging each numbers, and please the study about the change of each variables as CV and each station's cycle time and total cycle time. Also, the required size of the station, the number of stations. Okay. After your self-study, I will give you homework with use of this Excel sheet. Not this Excel sheet. By use of this concept, I'll give you homework with the actual Shunyard data. Okay. Oh, Christopher, also just 30 minutes. I'm sorry for too long class today. Anyway, this is the end of the topic about factory physics. Unfortunately, the limit, due to the limit of time, we cannot study about the about the blocking. Blocking means that we can also assign the predetermined number of the buffer size. In that case, the one more control variable can be assigned, but the topic is not treated in this study, except that blocking effect. We have studied about the chapter 8 of factory physics textbook. Today, I will upload the soft copy of the factory physics, and you can review about what we have studied about 2 weeks, about the queuing and the basic factory physics, and also finally what effect can be obtained from the variability.